Oh, okay, we're recording. So what we're doing right now, if you look at the syllabus, is we're dealing with the microcosm. And we'll have another section where we'll deal with the macrocosm, um, which is much more cosmology and galaxies and the start of the universe and so forth. So that's not for today. But those are the two extreme cases. What we're dealing with right now is the very small going uh, into the atom, and then with Ron going into the compartments of space itself to see what's going on. So and you can see what we're really doing is we're just describing a breakout of parts, and then this goes to that, or three of these makes up one of those. Okay, so it's just a taxonomy. It's a set of words, which is called Western science. And it's, we're not dealing with why. Okay, where do these numbers come from? Why are there three as opposed to, four or two? What's going on here? So that's, for another session. I've already blocked out the next couple of classes. So the class after this, we're going to be dealing with the geometry, which is really, I think, the thing that Ron and I worked on a lot, the geometry of the universe. And then the one after that, we're going to be dealing with the notion of, we talked about this before, information, and how information links everything to create, what Jung called the collective unconsciousness that linked everything together. But it appears to have tie-ins to modern computer science, and it suggests ways of using the language of computer science to describe what's going on. So we're gonna do that, and it leads you into the notions of what do you mean by consciousness? What do you mean by alive in some sense? What does that mean? So it gets into things that are, I'll just say, pretty metaphysical. And the thing to keep in mind here, I just have to go back in time. When I was in graduate school, my office was in this area with all these other high energy physicists, and we shared this computer that the Atomic Energy Commission paid for. And these guys were going to CERN all the time. They were doing these incredible calculations on this computer and simulations of all sorts, and then going to CERN and running these experiments, and then coming back and doing some more. And I mean, these guys were off the charts in terms of how smart they were and what they were doing. And when I remember the first guy passed his doctoral defense, you have to do an oral defense of your doctorate. And so he put a sign on their door saying, "The doctor is in." Okay. And then the next guy got past his. And so he took the sign down, he put a new sign up, "2 doctors, no waiting." Okay. and then the third guy passed, and he put up one of those things with those little 3 clocks, and they have hands on them showing hours for when each of them was going to be there. Okay. So that you could see, what was going on and so forth. So basically what happened then, there was a feeling at that time that with all of the work that had happened with before World War II, with quantum mechanics and going into the structure of the atom, and then dealing with this atom bomb and all kinds of particles being discovered that were all, if you will, resonances of a few basic particles, but they were all discovered and categorized. And it was described, that how these things are discovered are these particle accelerators. In the particle accelerators, you can imagine taking two clocks, and you take one of the clocks and run it around a circular track as fast as you can get it going. Well, let's mute everybody too. I think that'll help on the connectivity. Everybody just mutes if they're not going to talk. Let's see. So, sorry.
Yeah, don't take it personally. I will probably leave my camera off a lot. It just helps.
Yeah. Okay. So the thinking was they had gone through and come up with this notion that electromagnetism and gravity had been discovered earlier, and then the forces that held the nucleus together, the protons, are all positively charged in the nucleus. And we learned in electromagnetism 101 that opposites attract and likes repel. So what in the world is holding these protons together? So they concluded it was a different sort of force, which they simply called the strong force, because electromagnetism was the strongest known force. To have two like charged particles, two protons attracted to one another was incredible force. And then at the same time, they discovered these isotopes, which led to this weak force, where we'd have a neutron would decay into a proton and an electron. The electron would go flying off, but there'd be another proton now in the nucleus that would be bound there, and that created what was called an isotope of that element. And so here were all these forces: gravity, electromagnetism, strong force, and weak force. And the feeling was, boy, in another 10 years, we'll wrap this whole thing up and we'll put a big bow around physics and go on to something else. And all I've got to say is, 50 years later, that wasn't the right call. That they basically hit the wall, as we'll see, and have really made no progress. And that's why there's been this push, in part you see reflected in the materials in this class, to get the concepts that came out of the East to get into Western science. And it's led to a certain amount of arrogance or hubris with the people that are involved in this, because they're saying, well, look, we're dealing with the most fundamental stuff. We've got the parts nailed down. As we'll see, they don't even have all the parts right. Okay. But the arrogance leads to, so the handiwork of all this stuff is what I would call God, or I don't need a God to help me in doing anything. It's all been worked out in physics, and it's so beautiful. And that's probably not a good attitude to come up with new ideas thinking that way. It leads you nowhere. So let's see what we come up with here. Let me get the PowerPoint up. Easier said than done. Hold on. Okay. So here we are. Let's see where this goes. We're going to deal with precursors to what we're talking about tonight. People that very much took an Eastern path, not the path of Western science. And these are all things that you can find, they're documented and so forth. And then we'll get into what we saw in more detail with Annie Besant and Charles Leadbeater, and Stephen Phillips discovered their book was published in 1908, and I believe it was updated. And Stephen Phillips discovered that in grad school in the United Kingdom, sometime in the late 1970s, and he wrote up a paper critiquing this because he was dumbfounded that these people had done all this stuff, and it predicted a lot of things that had been missed. I just noticed there's a chat thing here. What does it say? Oh, I see. Okay. So Ronald Cowan had read Annie Besant and Charles Leadbeater's book, and he saw Phillips' paper on this where he was going through and describing, and catch me if I'm wrong, Bruce, he reached out to Phillips and he said, look, I've gone into deep meditation, and I've been able to confirm Annie Besant and Charles Leadbeater did, but in fact, I can go beyond it. So Stephen Phillips in the early 1990s came to Toronto and met with Bruce and Ron, and he tested Ron to make sure that things were on the up and up according to whatever tests he could come up with. And then they interacted a bit, and then Ron went off on his own. He has a number of things in his book, The Path of Love, Making Buddhism a Science, that you can buy the book on Amazon. By the way, it's available. Bruce, what do you want to say? You met Stephen Phillips, and he was there for what, a couple of weeks in Toronto?
Yeah, he was interesting. He was friendly, nice man. The test that he did for Ron is that he'd have a wire and batteries connected, and he'd switch the direction of the current. In other words,
without Ron being able to see it.
Yeah, without Ron seeing it, right? So
right.
Ron could meditate on the wire and tell which direction the electrons were moving. That's one of the tests that he did for him.
Right.
Yeah, he was. They spent quite a bit of time together. So.
Yeah, and Phillips has an extensive website with tens of pages, and he, being educated in the UK, they do a great job of educating them in geometry. And so he went back and he looked at everything and really pushed a geometrical analysis or a sacred geometry analysis of everything that he was seeing here, which I welcome you to go look at it. So that was the things the bulk of the things we're gonna cover here today. In the West, there were though two people, Louis de Broglie, who in the 1925 timeframe said, well, since we have things that behave like waves and they also behave like matter, why don't we simply say that everything is both a wave and a particle? Okay, and this was, shall we say, controversial. People said, well, look, it's either a wave or a particle. What are you talking about? But anyway, he stuck to this, and people had then done this double slit experiment. I'm trying to remember. I thought we covered the double slit experiment with a video. Yes or no? Susan, do you remember this? Patty? Yeah. No, you don't remember it. Okay.
This year, you mean? I don't think so.
Okay, let me go. I'll go cover that right after this, so you'll see what's going on. But the end result was there was another guy, David Bohm, whose thesis advisor was Robert Oppenheimer. And so David Bohm wrote a paper in 1952 saying, look, a lot of the things that you see going on here can be explained by what he called a pilot wave, that there's a pilot wave that runs everywhere and synchronizes everything. And so nothing's out of sync at all. And he called it the explicate and the implicate. The explicate is what we see. That's the world around us. But the plumbing the plumbing that's underneath it is called the implicate, and that's where this pilot wave lives, and that's in fact what Ron Cowan observed. So we're gonna touch on that. I'm gonna go back and touch on what physics came up with in the 1975 timeframe. It's now 2023 and it has not changed. It's called the Standard Model of Particle Physics, and so it encompasses a set of particles and a set of waves, and the waves have a name called boson, but a typical wave is, for example, a photon, a light particle. And so this is it. It's I believe it has, I want to say 17 things in it. As we'll see, some of them are redundant. And then we'll go off to what a brilliant physicist, Stephen Wolfram, came up with, which is very much a computational view coming at it from Western particle physics. And he calls it the rules of rules, or the ruliad. So it involves, you know, very high powered notions in information transfer and computation. And so we're going to on the right track as to where things are going. We still have a long ways to go to uncover these things. So
I just want to chime in that Stephen Phillips did a really good deep look at Kabbalah without being, you know, a fully initiated Jewish practitioner, but just looking at the sacred geometry of it all. And he makes it very accessible and understandable in terms of the geometric relationships, which is really the most important thing in astrology too. It's not the signs, it's the relationships between the planets. And we're not even really looking at the stars or the constellations. It's the geometric relationships between, we count 10 planets. We don't count the Earth because we're on it and we're looking out. So we do count the sun and the moon as planets. But it's all about what's called the aspects between them, which are their geometric angles. And so I thought Phillips just did a really great job of making that less occult and more accessible.
yeah, and one of the things that he concluded was that the mystics out of Judaism, the Kabbalists, were onto something, that they were seeing the true geometry of the universe around us. And we'll come back to that because it's amazing what they discovered through just, again, through meditation. I'm going to switch to the movie here, which is, here it is. It's called Dr. Quantum doing the double slit experiment. So here we go. I'm going to crank it up. Can you hear this? Can you hear it? Can you hear it? Everybody hear it?
Yes, and I don't remember seeing this, so.
Double
Okay.
slit experiment. Little balls of matter. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of Higgs. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. The electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. Behaving like a little marble, it produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So hold on, I have to shut that down just a second.
Did he say the electron decided to do something?
Well, you're saying the electron is there, okay, coming out of their electron gun, and if there's one slit, then the electron stays a particle and goes through the one slit. If there's two slits, as soon as the electron leaves the gun, the electron sees there's two slits and evidently turns into a wave. Except if you're looking at the electron, you're actually following it. If you're following it, then it stays as an electron, as a particle, and it goes through either one slit or the other slit. So this shows Einstein and other people called this why quantum mechanics is incomplete. They don't have an explanation for this, but that's what Ron Cowan came up with. That's what we'll see as an explanation for this. And that this experiment is already 100 years old.
Yeah, I mean, I remember
and
hearing about the experiment, but I just, it almost sounds like they're saying the electron has consciousness.
well, it doesn't.
Make the decision.
It probably does have a smidgen of consciousness, as we'll see. That's probably true. But the fact is, it's able to detect whether there's one slit or two slits, and whether there's an observer or no observer. And that means that there's an algorithm that it's using to decide, am I a wave or am I a particle? Okay.
Okay.
This is one of the conundrums that you come up with in doing these things. There's others that are also very spooky as well, but we'll get to them. So let me go back to, let me see if I can go back to the presentation, which is here. And we'll go to slideshow. Here we go. So this is what we're going to try and cover. We'll see how much of this we get through. So the first one that I put up there was Marco Polo, who took there was a so-called Silk Road. The Silk Road actually existed when the Roman Empire was in existence and China was there, because China had these purple dyes that the Romans liked for their official robes of different sorts. And so the Silk Road was created as a path for merchants to go to China. And it's still there today. And Marco Polo took it, maybe between, let's see what this thing says, 1271 and 1295. And he went to China, etc. And the thing that I wanted to leave you with here was he recorded seeing two swamis at a Silk Road oasis. How do I get rid of this thing? Let's see, put it up here. Yeah. And they levitated off the ground. The guy who owned the oasis said, Marco, I want to show you something. And so these two swamis just were sitting there 3 feet off the ground, cross-legged. And you can read this in the book. And Marco just, his book was, again, he's just recording everything he saw. So here it is. It's right in the book. And of course, everybody ignores it because what do you do with it? But I'm just showing there's a lot of things that are right in front of us that people choose to ignore. Now what? It doesn't want to. Here we go. Now, another guy that you've undoubtedly not heard of is an American. He was born in 1837, died in 1898. He spent a lot of his life in Philadelphia. His name was John Ernst Worrell Keely, and he claimed to have discovered some sort of new electromotive power that was based on something related to vibrations, which he produced from what he called an interatomic ether from water and air. So he gave a demonstration in 1874 where he blew into a nozzle with his breath. Then he poured 5 gallons of tap water into the same nozzle. And then when he got done, the pressure gauge indicated 10,000 pounds per square inch, which he was saying was evidence that the water had been disintegrated and liberated somehow. And then you could use this to do things like power a machine of some sort, and so on. Keely was a musician, so that's why he talked everything about vibrations and so forth. And he actually wrote a book that I went through, and my colleague who was in the black ops side of things really loved Keely. Keely clearly observed quarks, so just on his own. So he learned somehow to meditate, to see quarks, which are, as we saw, we need 3 quarks to make a proton and 3 other sorts of quarks to make a neutron. And another thing that was recorded, it's amazing what you find on the internet, was in the 1870s, he built a flying machine for the US Army. He decided he'd go fly it over to the Army headquarters in Washington, D.C., and he was flying this thing around, and they said, well, we have no idea what we do with this. You know, we're the Army. We fight on the ground. And, you know, and apparently Keely's flying machine could do 500 miles an hour. So Keely gave up, and he went off and set up a number of companies to try and commercialize what he did. And nothing ever really worked out, but it's an interesting example of what you saw at this period of time. There's another guy, John Babbitt, who you haven't heard of. He was a jeweler and a watchmaker, and was in New Brunswick, in Fredericton. I've been there. Bruce, have you been there to Fredericton? Oh, okay. Anyway, New Brunswick is next to Nova Scotia. Okay, it's a Canadian province, and other people that were there were, you know, for example, Alexander Graham Bell. I believe he's not from Nova Scotia. He's from New Brunswick, and there's actually, I went to a museum, an Alexander Graham Bell museum. It was amazing. Bell had all kinds of interests and things besides telephones and so forth. But anyway, Babbitt was fascinated with what Bell was doing with the telephone, and he evidently in 1879 produced one of the first electric lights in the town of Fredericton, and he participated in experimental work. And one of the things he did in deep meditation is he apparently observed subquarks, as we'll see. We have a picture of that later on. I'm just setting the stage here. Now we have Nikola Tesla. So Tesla's here. And what I'm going to do is give you a little different history. There was a German mathematician, Hermann Grassmann, and he wrote a book in 1845 called Electrodynamic. And this encompassed everything that James Clerk Maxwell did between 1861 and 1865, except that Maxwell gets all the credit for coming up with the equations that describe electromagnetism. Actually, Grassmann did it all in 1845, but no one could understand anything that Grassmann did. Maxwell was able to explain what it was going on, but he wasn't aware, to the best of my knowledge, of what Grassmann did. So what happened was, in 1970, when I was in graduate school, my thesis advisor asked me to look at this. So I looked at it. There wasn't any easy to get exposition of what Grassmann had done. So I did my own, which I actually wrote up, and it was published in 1974. So let me just go to that. Let me see if I can find that. Hold on a second.
Remember that Bart was at Bell Labs for how many years?
12 years. So this is when I was at Bell Labs. I published this. So here we go. So here's me, and this is, you know, this is the abstract for this paper that I put together. And we just go down here, and the thing that I did that Grassmann didn't do, because I'm sure it never crossed his mind, was I put all of it together into a diagram. Okay, all of Maxwell's equations are described in this diagram here. So let's see if we can make sense out of it. Starting out over on this side of the diagram.
Could you blow it up?
I can try and blow it up. Let's see. Yeah, okay. A little better. Over here, there's just a function of X, Y, Z, the three spatial dimensions, and time. But for time, I always use the coordinates of multiplying time by the speed of light. And that meant that the speed of light is in meters per second and time is in seconds. So I now had the speed of light times time. I now had meters. So I could have something that was the same as the measurements of length that we use for space. We use meters to describe how long things are in the X, Y, and Z directions, okay? And so basically, we started with this function, which is just a scalar function of space and time. And we took and calculated effectively the gradient of this function. Now, the gradient is how this thing will change in each of the three spatial dimensions and the time dimension. So we took the gradient here of this function and we came up with something else. Now this is no longer a scalar function. It actually now has an X, Y, Z, and time dimension to it. So it's now a vector, and each of the components of the vector become potentials in electromagnetism. If you do this gradient thing again, you come up with electric and magnetic fields. If you do it again, you come up with current densities, magnetic and electric current densities. And if you do it again, you come up with electric and magnetic sources. So that's every time you do this, I'm moving across this diagram this way, and I can go down this way as well. And this was something that was of great interest to mathematicians in the 1970s. It's called a commutative diagram, because you can go around it any which way, and you find out interesting things. So that's what I did. And when I did this, there's some turning the crank of various things. What's behind it is that there was no physics in this. Okay, I didn't do anything other than simply take this function of three spatial variables and one time variable and compute its gradient multiple times to come up with Maxwell's equations. So this is very strange, because there's no physics whatsoever, but I've got all of Maxwell's equations here. You could go ask Maxwell that, there's more stuff here than Maxwell came up with, okay? So that was the first thing that stopped me. And I realized—
It's showing how the universe works. It's
Yeah.
showing that it actually works with
Yeah.
those patterns.
Yeah, no, it is. It shows what's going on. But one of the things, I'm just going to go back here to, let's see, to this. One of the things that I didn't realize until, I'd say 15 years ago, but Nikola Tesla realized this, is what I'd left out of this. That is what Tesla realized. And we'll just come to that in a second. So here's what I put together. This is an Acrobat file, so we have to go through it like this. So the electromagnetic field is actually really generated by photons that are these particles, and they run in the ether, but the ether is actually space compartments. So the photons hop from one space compartment to another, and that leads to electromagnetism. Okay. Now, what's missing is this. If you take a look at, and you have to know some physics here, there's also an area of physics called fluid mechanics. And so if you look at the equations for an incompressible means if I squeeze it, it doesn't compress. there are fluids that do compress, and it's frictionless. The little pieces of fluid slide against one another. There's no friction. If we look at those equations, they're actually identical to the equations for electromagnetism, but there's a couple extra terms because of the density of the fluid. You know, that's why they're called equations for fluid mechanics. They're not called equations for electromagnetism. So a German physicist, Arnold Sommerfeld, you know, has a book that he's just pointing out exactly what I said here. The book's written, you know, in the 1950 time frame and so forth. But I just took this now, and you take a look at this and say, well, then, if this is the case, then why don't I include in the equations of electromagnetism that I just derived using what Grossman had, I add in terms to reflect the density of space itself. And that's the density of space itself. The space is the fluid that we're talking about that's making all this happen. The compartments of space are supporting the flow of the photons hopping around to create electromagnetism. And so if you do this, you end up with a full set of equations, which is also incomprehensible. So what you do here to try and get some money out of this is you do what's called a perturbation analysis, where you carry a power series. So the 0th order term, I take the density of the ether, the density of space around me, to the 0th power, and I end up with Maxwell's equations. When I take the 1st order and the 2nd order, these are things that are the density of the ether to the 1st power, the density of ether to the 2nd power, and I include all those terms, then what you discover is you end up with the additional terms giving me the strong force and the weak force. Now, what we got in Maxwell's equations, just to remind you, see if I put this here. No, I didn't. What we got in Maxwell's equations, remember, was that positive and negative attract one another, positive and positive repel one another, negative and negative repel one another. So that's what happens here. But it turns out when you go to this extra set of terms here, that you end up at very short distances, it flips and becomes a strong, the strong force, that positive attracts positive, negative attracts negative, positive repels negative, negative repels positive, and this weak force comes out of it as well. And finally, what's left that we call gravity is simply how the density of the ether changes as we go through things. So gravity isn't really a force. It's, as Einstein said, it reflects how the curvature or the density of space itself leads to what we call gravity. Now, this was, I'm just trying to see what else I put in here.
Do you
This-
have a picture of the space being fed by the?
I don't have that handy right now. I'm just trying to show you what's going on here. I'm going to go back to the PowerPoint presentation we're dealing with, which was here.
Do you have some on the resource pages?
Yeah, on the resource page, we have some. So let's see, where do we go? Slideshow. Oh, wait, sorry. I forgot to get out of share screen. No, I did get out of it. So hold on. Here's where I want to go. Okay. So this is a prelude. Grossman did basically what Maxwell did, but he did it 15 or more years earlier. I simply, regurgitated what he did and made the observation that there was no physics here. Maxwell did all of his work based on looking at the experiments of Faraday and many other people, and that's what led him to come up with these equations. What happened after this, the equations showed that it was possible to have waves propagate through space, and the waves had never been detected before, and so a German, Heinrich Hertz, went ahead and created a spark generator. Yeah, and he had a spark generator and a spark detector, and these generated sparks. So the sparks, because they're very abrupt, they have very high frequencies to them, and this ended up being the first demonstration anyone had that there were waves, that his spark transmitter could result in the spark detector picking up what's going on here. So there's several things to take away from this. We see that currently Western physics talks of 4 forces: electromagnetism, gravity, strong force, and weak force. But evidently there's only one force, electromagnetism, and gravity arises just as a change in the density of the ether. And all these other forces, the strong force and the weak force, arise from different, very short distances for electromagnetism. So someone did realize this. That was Nikola Tesla. So he went ahead and he decided to build a transmitter. And Tesla decided this transmitter would transmit power. He felt that it would cost too much money to run wires everywhere to allow electric power to be transmitted all over the place. And he said there's only 2 ways he could think of for sending electric power. One was through the ground. He tried that out. And the other was through the air. So he actually constructed out on Long Island a plant, and he went running around, tried to get money for this thing. And J.P. Morgan actually gave him $150,000 for a 51% share of what he had here. Among other things, Tesla said, you can use this to communicate with other people. So you can communicate anywhere on the earth, is what he was telling to, he never told Morgan that, by the way, it could also use this to send power anywhere on the earth. He left that out, okay? So he's building this thing, and there's a race going on between Tesla.
Move that bar over.
What?
See if you can move that bar over.
Move the bar over
Yeah, so you can see the top of it.
here?
Yeah, and I'm either having a deja vu, or you did talk about this a couple of weeks ago.
No, I don't think so.
I think you did.
No, this is there was another guy in Europe, Marconi, who sent a short message with a radio system across the Atlantic, and Tesla hadn't got his thing up and working yet to be able to do this. So he thought that Marconi, in fact, infringed on patents that Tesla had. And in fact, Tesla went to this all the way to the US Supreme Court, and Marconi had to pay because Tesla's patents covered everything that Marconi had done. But it didn't matter because Marconi was a great salesman, and he ended up carrying the day. Tesla had to explain to Morgan he wanted more money, but Morgan isn't going to give him any more money. And so the end result was Tesla kept giving it a crack, but he couldn't get this thing to work. And let's see. And people put money in, and then they pulled out, and he gave up, and the whole thing was demolished in 1917. So Tesla undoubtedly figured everything out that we just said here about the ether and what generates the strong and the weak force, and so forth. But a lot of that has been buried by our government. Tesla had filed, he was granted at least 700 patents. If you go to the US patent website today, you'll find 110 patents with Tesla's name on it. So the government has blacked out the other 590 patents. They refuse to, they say, for national security reasons, and that's where it's at. Okay, so this also reminds me of the story that in 1916, Einstein was giving talks all over the world on his new theory of general relativity, which was explaining that the curvature of space would lead to what we call gravity. And he decided to give a talk in New York City, and Tesla showed up and sat in row 1 and dead center. And Tesla listened to everything Einstein had to say. And then he went up to him afterwards and said, you know, this is really beautiful mathematics. I really applaud you for this. It's just totally irrelevant. And Einstein didn't know what to make out of this, other than several years later, someone came up and asked Einstein, what's it like to be the smartest man in the world? And Einstein said, I don't know, you have to go ask Nikola Tesla. So that's where that goes. So this takes us back to the work that was done under deep meditation by Annie Besant and Charles Leadbeater, where they're going down and they're trying to look at not simply atoms, but what are the piece parts of atoms. So the idea here is, if we have an atom, what makes up an atom? So we concluded that was an electron, set of electrons, and a nucleus, and the nucleus itself was made up of protons and neutrons. And that appears to indeed be the case. But they went much further than that when they published their book, Occult Chemistry, that they were working side by side in meditation. So they checked each other on what's going on. And in the book, it's clear that they observed subquarks. So 3 subquarks make up 1 quark, and 3 quarks make up 1 proton, or 3 other types of quarks make up 1 neutron. And so this was done in 1908. Right now, no particle accelerator can reach the energy levels that would be required to show that quarks are made up of subquarks. So this is something that they observed. They were able to draw pictures of it because they had paper and pencil, but it hasn't been experimentally confirmed, quote unquote, by anyone in Western science. The other thing that's crazy about this, though, is that in their meditation, they always saw double. So instead of seeing 9 subquarks per proton or neutron, that is 3 make up 1 quark, and then 3 quarks will make up 1 proton or neutron, they always saw 18 subquarks there that was going on. And this held up over, they looked at every single element in the periodic table of elements. So they're always twice what is actually going on. And I asked Ron about this because Ron didn't observe this. When he observed a quark, he saw 3 subquarks. When he looked at the proton or neutron, he saw 3 quarks. So he didn't function this way. There's something about how they meditated that led them to doing this. Another thing that they did here was they're the ones that came up with this notion of what are called isotopes, that some of the elements that they observed would have the same number of protons and electrons, so that everything would cancel out. There would be no net charge on a given atom, but they would have differing number of neutrons, and this led to having things called isotopes for a particular element. So hydrogen, for example, simply has 1 proton, and that's the most common isotope of hydrogen. But there's a second one called deuterium that has 1 proton and 1 neutron, and a third one called tritium that has 1 proton and 2 neutrons. And then there's a lot of other isotopes that are unstable. These can actually be observed, everything here. Another thing that Leadbeater and Besant did was they noticed that the subquarks actually are made up of 10 closed strings, and the strings contain resonating energy. So the subquarks themselves aren't really particles. They're these 10 closed strings that have some jelly in them, and they're spinning like crazy and vibrating like crazy. And finally, unlike what Ron Cowan did, they really didn't observe anything what's called dark matter, which we'll come back to in a little bit. But these are, huge accomplishments, and this is done in 1908.
And a lot of their postulations were confirmed by the science later.
Yeah, that's what excited Stephen Phillips, was he said, wait a moment, they developed all this way before we did. In fact, the notion of quarks was only developed in the 1960s in Western science, and here they were not only with quarks but subquarks. Now,
And a lot of it was mathematical. They were just looking at the mathematical patterns and kind of filling in the blanks. And later something would be discovered there that they anticipated just logically.
Yeah, absolutely. So here's a picture of a subquark. There wasn't any such name then, so Leadbeater and Besant called it an ultimate physical atom, because this was the fundamental component that they found that made up what we call matter. I mentioned this other guy, Babbitt, in New Brunswick. He actually wrote up a book, and in the book he had a picture here of what he called an atom. It looks remarkably like what Leadbeater and Besant had. Okay, it just doesn't have the same detail. They have incredible detail here in terms of counting these strings to see that there's 10 closed loops here going around here, which Babbitt didn't do, but it just shows that Babbitt was onto something. He just didn't carry it as far. There's also the thing that it's called chirality. If I take my hand, if you can see this, I have my thumb that's up, so it curves around this way, or I can take my thumb and go down, and then it curves the other way. So there's a left-handed and a right-handed chirality that comes with these strings, and they observed both of these that were there. So did Ron Cowan. When they got around to looking at a hydrogen nucleus, okay, here we saw that the things were paired up, that they had too many. Here's one of these subquarks here with three what do I want to say here? Here's the nucleus, which is a single proton, okay, and in the single proton should have 3 quarks in it, and each of the quarks should have 3 subquarks. Well, they've got too many. They've got 1, 2, there's 9 here is what they observed, and then this one over here has another 9, so they've got twice as many of these in a single proton. And for example, one of the reasons this might be is when they're doing this doubling thing, hydrogen in the world that we live in doesn't occur as by itself. Because of the nature of its chemical structure, hydrogen binds with other hydrogen atoms. So hydrogen, when we play with it like as a gas or a liquid, it's always has 2 atoms to it. Okay, and that was simply a conjecture that led to them observing this double here. But who knows? I don't know what happened. But even so, this is showing this is the so-called strong force at work holding these subquarks together to go do this, because the subquarks have different charges and they all want to go in different directions. And as an aside, this is something that really wasn't explored, but they looked at all of the different elements, and they categorized them as with these quarks in there and subquarks as being having geometric structures. One was a spike, one was a dumbbell, one was a tetrahedron, one was a cube, one was an octahedron, one was a set of bars, and one was a star. And they observed these repeatedly in different nuclei of different elements. And I'm not aware of anyone pursuing this at this point in time. But again, I don't know everything. So they just did this to allow them to create their periodic table of elements, which they use this structure. Here's the spike group, the dumbbell group, the tetrahedron group, the cube group, and so forth. So these groups that are here are characterizing how the nucleus looks, okay, which is not the way that we end up constructing a periodic table. We look at how many electrons there are. Is there 1 electron, 2 electrons, 3 electrons? And that's how we construct the periodic table of elements. So this doesn't look at all like anything we're familiar with, but it was complete. It predicted what was going on. And here's a huge chart. You can see up here is hydrogen, and here you can see they had 18 of those subquarks in it, okay? And then everything, 18, 36, 54, 72, everything is a multiple of 18, going through all these elements in in what they observed. And as you can see, there's some counting errors here. You can see that this is what Phillips did, was he noted like this one didn't seem to match. It's off by 89. This one's off by 22, but most of them match exactly with this formula of 18 times 1, 18 times 2, and so forth. You know, so it's an incredible achievement is what they did here. Now, let me get out of this. Oops. And here's a graph. You can see how well it fits. The guy that reviewed the paper that Phillips included all this in, you know, thought that Phillips was a complete kook, and you know, just discarded everything that Phillips had to say. Just as a reference, this is a way to display the modern periodic table of elements, and you can line that up against what Poisson and Leadbeater did, and see that they actually predicted things that are showing up here as holes in the actual periodic table of elements.
Still today.
Yeah, till today. Now, another thing that came up in all of this, I'm going to do this in advance of the next class, is what was going on in Western physics. So there was a key person, Richard Feynman, who was at Caltech for many years, and he decided to look in 1962 at is it possible to come up with a quantum theory of gravity? The problem that they'd always had with gravity was it was a force that takes place on very large distances, miles, millions of miles, whatever, and this allows the planets and suns to all interact with one another. So it's a theory of the very large, but quantum mechanics is a theory of the atom, okay? So is there really some way to bridge these two things and to come up with a quantum theory of gravity where there would be some particle which would be called the graviton, and that would be the thing that carries the force of gravity. And so Feynman went through this and investigated. He tried to come up with giving spin to this quantum particle, this graviton, which had no mass, but it has spin. And if it had no spin, he couldn't come up with any self-consistent theory. If it had spin 1, he couldn't do it. But when he came to spin 2, then he came up with the equations that Einstein came up with for general relativity. But that was where he dropped it. He didn't think there was anything more he could do with this. And you know, Feynman is an incredible physicist who, you know, can do all kinds of things that mere mortals couldn't do.
What do you mean by spin 1 and spin 2?
Well, you have the ability spin zero means that it's not spinning at all. What's spin one and spin two means that there's some basic unit of spin, whatever it is. It could be 3 spins per second, and that's what you find in quantum mechanics. Everything is discrete. So to have spin one, you might have just 3 spins per second. Spin two, you'd have 6 spins per second. Okay, it's twice as fast. But there wouldn't be any spin 1.5. There wouldn't be any spins 4. They're all discrete numbers. So spin 0, spin 1, spin 2 was what Feynman said. You have to look for something with a spin 2 theory to be able to explain what's going on. So we come to this chap, Claude Lovelace, who passed on, back in 2012. He never got his doctorate, but he started working on this stuff, and he was coming up with all kinds of equations for things that involve closed loop strings, okay, which is what Leadbeater and Berzana observed. But there were other people who were dealing with strings that were just flapping in the breeze. They were open-ended. So he dealt with closed loop strings. He was trying to see what would happen. And so when you went ahead and did this in 3 dimensions for space and 1 for time, then you ended up with new particles appearing called tachyons. A tachyon has the ability to travel backwards in time, and it travels faster than the speed of light. Okay, so it's a very strange particle. No one's observed any tachyons. They could very well be there under some circumstances, but he was faced with this problem of his theory had these tachyons in it, and how does he get rid of it? So he did something that was unusual. He said, well, I'm doing this in 4 dimensions, 3 for space and 1 for time, and I think I'll increase the number of dimensions. So there had been work right after Einstein came out with this theory of general relativity for which was in 4 dimensions, where someone named Theodore Kaluza said, well, I can add 1 more dimension, a 5th dimension, and I'll come up with electromagnetism as well as gravitation, okay? And Einstein looked at this and he said, I don't see anything wrong with what you're doing. Who knows, maybe you're right. And Einstein himself worked on this in this 5-dimensional theory. So it's not out of the question to add extra dimensions. But Lovelace didn't stop at 5 or 6. He increased the numbers until he got to 26 dimensions. And then when he got to 26, all these problems disappeared. But he had a 26 real dimensional space for what we would call photons or bosons, and that matched what's going on for the observations that Ron Cowan made under deep meditation. So we're leading up to, there might be something here. The proof is that someone like Ron has observed this and says, yeah, it looks like it's 26, but that doesn't do any good to a Western physicist, because there's no meter that you can put on that says, here, I'm going to count dimensions. So my dimension meter doesn't exist. And where are these dimensions is another question. That's what we're going to deal with next time. But just to jump ahead, what Ron came up with was that we have matter here that we deal with, and we have 4 dimensions, 3 for space and 1 for time. That is what we think of as everything. There's another 6 dimensions that are right around this. We'll come back to where this comes from. So a total of 10 dimensions take care of matter. 10 dimensions over here take care of dark matter. And then there's something here that connects the two to make sure that everything works okay. And this is really, a huge contribution. And Ron came up with all kinds of numbers that we'll talk about and so forth. But this is what appears to be the universe. So when people ask about this, they say, well, when I go and meditate, I go into deep meditation, then what happens is I'm basically in this area here, of 3 space and 1 time dimension. And I could think of this as watching a movie. So all of a sudden, when I am under deep meditation, I can think of myself as stepping away and sitting out in the audience. And out in the audience in the movie theater, I realize it really is a 26-dimensional space. It really is. But you know, I can only do that under those circumstances, and I can watch the show that happens here in the 4-dimensional space-time arena, and so it goes. So, Bruce, what would you say about this?
Ron and I didn't talk about this very much.
Right.
He was
It's
He
not
was
the
very
sort of thing
inspired
that
by
lends
the-
itself.
Huh?
Yeah, it's not the sort of thing that you can talk about, because it's still hard to see these other dimensions, which you
Right.
can see. You could see they're there, but so what? What do I do with them?
right.
Yeah, right. I think Ron was very much interested in the particle side of things, as opposed to I'll just say the sacred geometry side of things. But we'll come back to this. This is for next class. So just to summarize what's going on here, Newton said, well, there's 3 dimensions for space and 1 for time. It's obvious. Just take a look at what's going on. Einstein in 1905 said, well, actually, the 4 dimensions here, 3 for space and 1 for time, are actually coupled in some way. So in fact, for example, if you move in space faster and faster, say approaching the speed of light, and you have a clock, it slows down. So time is influenced by space, by how I move through space. This is a tip-off. There's something deeper going on here. In 1916, Einstein did his general relativity, showing that the curvature of space results in what we call gravity. The deeper the curvature of space, you know, the greater the gravitation is. So the sun distorts space more than the Earth does, and the Earth distorts it more than the moon. But the thing that comes out of this is the stronger that gravity is, the slower time is. Okay, for example, very strong gravity is what is called black holes, and no one knows. You might take forever. You think your clock might slow down forever as you try and approach the black hole and get in there. But a more simple way to think about this, if you had a clock on the top of your head and a clock down in your socks, then the clock on the top of your head is running a little faster than the clock in your socks. Because why? Because your feet are closer to the center of Earth, closer to where the gravity is, and your head is out a little bit, so you know, away from the Earth, so the gravity is a little less there. So this led to, in 1970, having 26 real dimensions for these bosons. Let me just go back to this. So we have matter here in these 10 dimensions, and the photons bounce all around in all 26 dimensions. Okay, that's what's unique. And what we call dark matter, we'll come back to, is just here in 10 dimensions. Just a prelude to what's happening. In 1980, there was a lot of work in what's called string theory, and it suggests that we have 10 dimensions, maybe 11. One of the things to keep in mind about string theory is, unlike these other things of what Newton did or Maxwell or Einstein, string theory has yet to write down a single equation. You have a theory with no equations, okay? And then to make it even worse, string theory has been able to find no experimental evidence that it works, other than to come up with an experiment like, let's start the universe over again and see what happens, which is not really an experiment. We don't know how to run that experiment. But anyway, the string theory is there because in part, it's the best thing that they can come up with to describe what's going on in the universe. There is no better theory available at this point in time. For 50 years, it's been the only one. And the other thing about string theory is it's what Annie Besant and Charles Leadbeater, what Ron Cowan, what Babbitt saw, what what's his face, Keeley saw. They all saw strings. So they're on the right track. We just have a long way to go here. And this results in today. I mentioned that we have, this was done in 1975. Okay, so there's been no change in this since 1975, but we have things called quarks, and there's 6 types of quarks, but actually there's only 2 types of quarks, and these others are resonances or higher vibrational states of these quarks here. We have an electron and, if you just take a look in Wikipedia, you'll see that you have 100 billion neutrinos going through a square centimeter of your body every second. 100 billion. There's more neutrinos in the universe than anything else. And one of the great debates has been, is there any mass to the neutrino? And it looks like there might be some small mass to it. And since there's so many neutrinos, that would have a huge impact on physics. But the net of it is we have the neutrino here and the electron here, and then we have these other 2 things that are actually resonances of these things here, that these things go into higher energy states and produce these things. So there's really only 2 quarks and an electron and a neutrino. And then finally, we get over here to what are called forces or bosons, so they're called. And so we have this gluon, which is the strong force. We have the photon, but we argued that the photon created the gluon, and the photon creates these other 2 as well. So there's really only one here, the photon. So we've got it down to 2 quarks,
Which
electron
is a unit
and
of light, right?
the what?
Is it a unit of light?
The photon is a unit of light.
And that's
But
why it's called a photon.
Yeah, it's a discrete particle. The thing that's unique about the photon is that the energy for the photon is proportional to its frequency. So therefore that is a tip-off as to the massiveness of the photon. So the higher the frequency, the more massive it is a way to think about it. We also had something way up here called this Higgs boson. The Higgs boson is unique in that it actually is a multiplier. We have masses for these things here, for the up and down, etc., masses for all these things, but they're all multiplied by what the Higgs boson value is. And this is one of the great achievements that Ron Cowan did, was he actually observed the Higgs boson. It occurs when the universe is created, when we have this big bounce, not a big bang. This Higgs boson is created, and that gives mass to all of these different things. When the Higgs boson hasn't been created, there's no these things exist, but they have no mass. So you say, well, if they don't have any mass, then do they really exist? Which is a good question. So anyway, this is what we're going to be dealing with going through this. Basically, for 50 years, people have been able to measure the charges for these things to 5 significant figures, and 10 years later, they measure it to 6 significant figures, and 10 years later, they measure it to 7 significant figures. But there hasn't been any fundamental change here in any of this. And in part, that's why this class, why there's a need to look to new approaches, which would come out of the East, is what we think, that is shown by what Besant and Leadbeater did, what Ron Cowan did. I'm just summarizing here what I just told you all about the particles, which are also called fermions, and then the forces, which are called bosons. So there's really only 2 types of quarks, 2 types that the leptons, there's only an electron and a neutrino, and there's a photon and a Higgs. So it's a very simple thing for matter. There's not a lot of parts here for matter. Stephen Phillips, here that he created this graphic that we've been using, discovered this, and you can go, I can provide you with this article here where he summarized all of the work of Leadbeater and Besant. And then finally we get to what Ron Cowan did. Now, do I have the date right here, Bruce? Was it 1941? Okay. And what I did was, and this shows you how the world works, was I was doing my usual thing on the internet, which is rummaging around, and I came across this Leadbeater and Besant thing, and like Christmas time of 2016. And Google existed then, so I went ahead and I started looking, and I found the work of Phillips, and then I found the reference of Phillips to Ron Cowan. So me being the shy person that I am, I simply picked the phone up because I could find on the internet Ron Cowan's phone number. And I called him up and I said, "Hi, I'm just reading this thing you wrote here, this book, and this is really amazing." Okay. And so we started collaborating and working together until he passed on in 2019. I never actually physically went to Toronto and met Ron. Okay. But what Ron did to go beyond what Leadbeater and Besant did was he observed both matter and dark matter. Okay. And he didn't observe them as pairs like Leadbeater and Besant did. He saw a single electron, he saw a single proton, he saw a single element of dark matter. That he was able not only to observe these particles, he was a very good artist. Okay, so he sketched these things, but he could stop them. What? He could stop them from vibrating. They're vibrating like crazy, and so forth. Now, I put in here that Ron observed the 7 chakras of the human being. Okay. Now, I'm going to just hop off here for a second. I have here, let me get it up here. I have in Kindle, I have his book, The Path of Love. And if I go here, we can all see it. So in this book, which is the end of the book, Ron says the following: according to my sketchy investigation of the evolution of intelligence, let me get this out of the way. The chakras and nadis evolved to their present form long before any biological life took shape in our solar system. So this means that their sophisticated structure and organization evolved in response to the world of dark matter or shadow matter. Their organization is so complex that when I used my meditation capabilities, my clairvoyance, to zoom in on the microscopic level to discern the function or purpose of any of these structures, I would find a function slightly different from the function of adjacent structures, and would have taken me thousands of hours of observation to discover the functions of the chakras and nadis. I simply didn't have the time available to me, so I'm simply going to document here the visual shape of the structures I could see. So here's the crown chakra, which is actually in color on the cover of the book. We've been using it. It's up on the. We'll go back to the PowerPoint. You'll see it's in the upper right hand corner. So here's the crown chakra, the third eye chakra, the throat chakra, the heart chakra, the water chakra hidden behind the fire chakra, the water chakra behind and below the fire chakra. The water chakra has an oval shape here, and the sexual chakra for the female is very different from that for the male. End of story. So the sketch of the root chakra is he's got in here, there's grass-like structures that extend upward along the surface of the body. So I'm trying to see. Let me just blow this up so I can get. That isn't too good. Here's A. So you can see on the surface of the body is where this is. The fan-like structures extend outside the body, and then there's grass-like structures that extend downward. So all of this is in the book. You can get the book and read it for yourself. This large disc-like vortex, small disc-like vortex, and then a large vortex that extends to the ground. So there's clearly some amazing things going on here. He did what he could for observations and concluded he just wouldn't live long enough to be able to shed any light on this. He didn't, and there's nothing, when I saw this, I asked him about it, and I couldn't think of any way to quickly cut to the chase and do some observations that would lead to something interesting. But we'll come back to this. We're not done with it yet. So let me go back to.
He knew he was sick with cancer at that time. I think that's really moving.
Yeah. Here I am. So you see up here in the top right of the slide is the cover of the book from Amazon. So this is in color. Everything that I have in my Kindle book is in black and white. Besides observing these 7 chakras, they're made up of what is called dark matter, and we'll come back to that. The basic thing of dark matter is that it's really subquarks that have no charge to them. Okay, so dark matter, the only interactions that dark matter can have is through things like gravity or being heated up. So they resonate, they bounce around some more. But what happens is when you get to a certain number of these dark matter subquarks, and we'll see sketches of them, you end up achieving sentience. So you end up with things there that the thing to keep in mind is these for the subquarks from both matter and dark matter, they live forever. There's nothing that we know that destroys them. Okay, but what happens with dark matter is that they create sentience. So they create an energy field, which leads to this notion of spirits or souls or entities that can achieve higher dimensional activity than we've achieved so far. So this is not a minor thing here. Ron looked down into the size of space compartments. Space compartments are typically 10 to the minus 33 meters. A nucleus of an atom is typically 10 to the minus 10th meters. So they're 20 orders of magnitude smaller than anything there. That's how small space is. But what he observed was that the space compartments are covered with blocks of information that are constantly scanning their surroundings. And this foam of space is made up of these space compartments. And he noticed that each space compartment could really only hold 2 particles. When you see this, typically one of them has a spin that's up and one of them has a spin that's down. There's some characteristic of them that is opposite, and so it goes. So he actually observed that as well. There's many more things he observed.
Why don't you show some images from the
I'm going to right now.
page?
So
Sorry.
So here we go to the electron. Okay, so I'm going to now skip over to, hold on, not here, here. Okay, so I go here to the electron. These are all pictures from Ron's book. It's on the resource tab. So over here
Of our website, Aleph Talk.
yeah, on the Aleph Talks website, here you can see he saw 10 closed strings here, and inside the 10 closed strings that made the outside of the electron, energy was resonating. So it filled up with this jelly-like thing that's there inside the electron, but it has a hole through the middle. So it's actually a donut or a torus. You can see different pictures of the hole. And then the outside of the electron, as well as the inside here, is covered with these blocks of information. So they're scanning, scanning, scanning all the time. So what happened in the double slit experiment? The scans are taking place, and they see there's one slit, so the electron goes through as a particle. As soon as the scans from these information blocks detect that there's two slits, it immediately becomes a wave.
Or it starts behaving like a wave.
Right, behaving like a wave. Okay, and you know, but this is, you know, you can look in every physics book you want to. You will never find a picture of an electron. Ron Cowan has a picture of an electron here, and what happens with this when we get into it. So we're just looking to see if there's anything else here. Here's an observation he made of a proton. So you can see that there's a proton has 9 of these subquarks in it, 3 quarks here, 1, 2, 3, and then each of the quarks has 3 subquarks in it, and so forth. And there's a little dimple here in these things as well. I'm going to look here just for a second. I think he had some good, yeah, here we go. When we deal with dark matter, what he noticed was you have these subquarks for dark matter, and they start to aggregate together, and they form something like a fern. So this is what it kind of looks like. And he just watched it for a while, and it immediately started to grab onto other pieces of dark matter. Remember, there's much more dark matter than there is matter. 5 times more. So all of a sudden, this thing looks like a gigantic firm here, and it's achieved sentience. He calls it a mind form. What, Bruce? What would you must have talked with Bruce about with Ron with mind forms or not?
No, I didn't. The only
Okay.
covers, yeah.
Okay. Yeah, I was left with the impression that, for example, our souls are in fact these mind forms in some level of energy.
Isn't that a Buddhist concept?
What?
The mind forms.
Uh,
I'm asking.
no.
It isn't?
No, I don't think so.
no.
Buddhism has the notion of soul, but
Right.
it doesn't, and a reincarnation, but it doesn't have.
I thought it spoke about the evolution of the mind form, the growth, or the
The only thing I would say is, you know, remember the thing to keep in mind about dark matter that I just touched on was, in order for it to be active, it has to have some sort of like thermal energy or be attracted to something else where it's vibrating, and it can end up therefore being sentient. But if it doesn't have this, like if it's just floating around in space, then it just shuts down. So Ron observed tubes out in outer space that are thousands of kilometers long that are made up of mind forms that are just hibernating. They're waiting to get close to something where they'll be able to get energized and go do something. And that's in fact how Ron ended up on Earth. He said he was on some other planet someplace, and the star for that planetary system went nova and blew Ron's planet to smithereens. And so Ron was drifting through space and he landed on Earth. And here we are. So you never know what'll happen. He said, look, he was minding his own business. It was a perfectly good place to be, and so forth. But we'll be coming back to this stuff. Let me just try. I want to go back to the PowerPoint here now that I've done this. I think we're about done for the night. I just want to make sure. Here's the electron we touched on.
And the blocks of information.
The blocks of information here that are scanning. We don't know the energy that's due to the scan, like where does it come from? And it apparently goes out to the far reaches of the universe almost instantaneously, so that when the electron is scanning the space around it, it's a piece of something that's missing from the standard model. It's not included anywhere. And another thing that came up with his observation, we have these matter subquarks, and they end up having fractions of the electric charge found on a proton or an electron. And there's 10 closed strings that go with matter. Dark matter has no electric charge, but they have 5 closed strings, so they don't resonate as much. They have energy inside them, but they have to be excited by some sort of mechanical or thermal vibration, and then they start to achieve the sentience that we talked about. These are, showing us chirality. Here's the information we talked about. Here's how this thing is growing. All of a sudden, end up with this huge thing here. But it's again very small, because remember, the dimensions for this are fractions of an atomic nucleus. So even though these things look huge, they're not huge relative to what the scale that we deal with. And so this picture here that for 50 years has sat here is incredibly incomplete. Okay, Western physics hasn't begun to actually do the physics required for all these other things that Ron Cowan and Bassan and Leadbeater and who knows how many other people observe these things. But we start to see what's going to be needed to go fill out the rest of this picture.
It would be interesting to look at more, so-called indigenous cultures.
Well, the
shamanic visions and things.
Yeah, the ones that we saw, the very mystical Kabbalists are the ones that see this sort of stuff, and that's a tip off. The shaman in Africa, in South America, and the Australian Aborigines, who knows what they're seeing. Okay, I'm just putting words around this. I'm connecting this to that, and each end of this and that have words in Western physics and how they get connected. But there's nothing more to it than metaphors. There's no. I'm not writing down any equations and trying to quantify how great the interactions are going to be for doing these things. So,
but these are working models.
Yeah. But
Bart, how do you define sentience or sentient? What does that mean to you?
say that again.
Sentient, how would you define?
What does it sentient mean to you?
Dimension. Dimension.
Sentient.
Sentient.
Yeah.
Sentient. I honestly think it's going to be algorithmic. Okay, you'll get enough of these things, you'll have enough little algorithms going that they'll start to interact in some way as is what we would call artificial intelligence. Okay, but that's at the just at the very lowest level. Okay. The reason for saying this is that if you have hundreds of millions of years or billions of years to go do this, who knows what you're thinking? Okay, you could be constructing things that are just literally inconceivable. We have no words to talk about for these things, and that's what I see is the real issue here. One of the problems with dealing with this computer model is the well-known incompleteness of it all. That if you in computer terms, if I give you a program and I ask you, can you show me, will this program stop or not? Will it halt? There's lots of programs I can show will halt, but there's some programs that I can show that I don't know the answer to. So as an example, you have the program which says whatever this man says is false. Well, if the person says something, then it's false. But then the statement is now true.
This was a Star Trek
if the
episode.
statement's true, then it's not false. And so you end up with a meta conundrum here, that you have something that you're talking about that you can't talk about. It's beyond the scope of whatever structure it was that you built. And I think there'll be more examples of that as we get into this, but we just haven't got there yet.
So it's different than the standard definition of like the ability to perceive or feel something. You don't mean sentient in that way, or sort of.
No, I don't. No, I mean it in the sense of being able to do philosophy, being able to be Socrates, to pose questions and ask and answer questions that would bootstrap me up to higher and higher levels of questions. That's what I mean for it to be. But that's me. You might have your own definition.
So that's consciousness, really.
Yeah. We're going to come back to consciousness too. I think consciousness is above this.
I think consciousness is different from sentience too.
Yeah. Sentience. I think it's possible to be sentient. For example, you can reincarnate as a stone. So I'm in this stone. It's kind of boring, not a lot going on, but it's nice and quiet. I'll be there for a while, and then the stone gets pulverized. So then I got to, go back and ask how to reincarnate, or I could be, a mosquito, or I could be a giraffe. These are all other things I could be, and they all have their own different versions of what I would mean by intelligence versus sentience. Okay, I would say the stone is alive because it's got some heat to it from Earth. So
it's said that they do perceive, they are vibrating, but I think of it as just as awareness.
Yeah. But the awareness in the sense of there's something out there and you're trying to describe it. You're trying to attach labels to it of some sort, whatever it is.
But you're using that term.
You can't just.
You're using that term when you're talking about electrons being.
Yes.
Sentient.
Yeah, that because in part they're coded with these blocks of information. So it isn't necessarily the electrons, which are I was strictly speaking would be the strings and the energy inside it. It's the blocks that are coding it that have all these algorithms in it and have the data. So they're always scanning, and I've got to update my data because now something just happened over here and something's happened over there. So that's always going on. And
that could be purely mechanical.
Yeah, it could be purely mechanical, but there could be something beyond it. I don't know.
But it seems that particles, whether they're particles or waves, do have some perception. whatever we want to say about.
Yeah,
The perception, we don't
I'm
know what
gonna
leads to that.
try and do this not in the next lecture, but in the lecture after that. I'm gonna try and deal with this sort of stuff of consciousness and what does it mean to have a mind, and these are all questions that that Ron was wrestling with, trying to come to grips with.
But the particle seems to modulate its behavior depending on its perception.
Whether it's being observed.
Right,
Right.
of, given conditions.
Yeah, no
it's
one
like,
no
how
one
does
told the
it-
electron it was being observed. It discovered it all by itself.
So it sounds anthropomorphic, but maybe it's just some mechanical, camera kind of thing that it's got that is triggering some other
Yeah.
reaction that looks like we're anthropomorphizing it as a decision that it's making, which maybe it's a simple reaction, If this clicks and that clacks and then this happens and we go to
Right.
the left and if this happens, we go to the right. It may be very, as I said, mechanistic, but it seems to involve some kind of perception and some change in what we're calling behavior.
Yeah.
But maybe it should be just action.
Yeah, there's another side to this which we haven't touched on, which is that it's unusual how mathematics appears to be such an appropriate way to describe all of this stuff. Okay, in fact, it's like too good to be true. Like if it's
Spoken as a true physicist, too good to be true.
well, just that the math side of things leads you into the algorithmic side of things. Okay, and I think, as we'll see here, what we call mathematics is undergoing a revolution right now, as it's discovering. To me, when I got out of graduate school, mathematics was 100 different silos and 10 mathematicians in each silo, and I don't think that anymore. I think there's bridges between all these things that are being discovered, and that's a tip-off as to that this is a real natural way to describe everything all around us. But we're only a small ways down the road. We have a long ways to go.
But it may just be how we're hardwired to
Yeah.
do it. So then we're projecting everything according to those patterns.
Yeah.
That we can't help seeing, and that's how we see everything. Whereas the other creatures, aliens from some other dimension or planet may not see things in those.
Or not
Patterns.
necessarily see things, but their whole framework for how they deal, for example, they just deal with the images to start with. So anyway, so Susan is going to run. So night, thank you for coming. And any questions, just give a yell. This is, as you can see, this is why we decided to teach this class, was to get out in the open, things that are really not talked about. And we'll see where it goes. We're not there yet. So have a great weekend, and we'll take it from there. Bye-bye. Get some sleep, everybody. Okay.
Happy trails.
Yep. Bye-bye.
Bye.